everybody, so you should have at this point started your station notes that were attached. What we're going to do today with this video is introduce free body diagrams and then kind of go over the first couple questions on the identifying forces worksheet. So just to try to get you in the groove of things. So I'm going to go ahead and share my dot cam here for you. And so you have this attached in Google Classroom. And I figured we'd just go over these notes together very quickly and then go over the few questions on the identifying forces worksheet just to get you through the rest of the day here. So this document here is going over the most common types of forces that we see in a free body diagram. Now, a free body diagram is a picture that represents all of the forces that are acting on a situation. Now, on the back here, we have a practice story problem that is depicted with a free body diagram. We have a box that's pushed to the right with a force of 10 newtons. If the force of friction is 5 newtons and the weight of the box is 2 newtons, draw a free body diagram, FBD, of the box. So when we draw a free body diagram, coincidentally, the object that was in question here is a box, but in general, it doesn't matter if it's a box, a person, a car, a pizza. It doesn't really matter the shape. Whatever the depiction is in the free body diagram, if you're drawing a basic one, we always just draw it as a box. So they're kind of nice, easy, lazy drawings, essentially. Now, this free body diagram is supposed to show all of the forces that are interacting with this box. And so assuming we don't have any special conditions, forces come in pairs. And so anytime you draw a vector in a particular direction, there should be a paired vector in the opposite direction to go along with it. So we draw this box where there is a push to the right with a force of 10 newtons. So when you're depicting forces, you always start in the center of the box, and then the vector arrow is drawn outward towards the direction of which the force is applied. So in this case, if the box is pushed to the right, I draw my vector arrow starting in the center of the box, and then it exits and it points in the rightward direction. And then I'm going to label it with the magnitude of the force. So this was 10 newtons. And then I'll label the force. So F there representing force, and then a little subscript to distinguish what kind of force it was. So it was a push, so I can call it F push. You might also see too FAPP or F applied for anything that is resembling a push. So now forces come in pairs. And so I have a force of friction that is going to oppose the motion of this box a little bit. So we have the value of that there. Now, friction is created when two surfaces rub together. So any surface that you have has some abnormalities to it. It's not a perfect smooth surface, so there's always going to be irregularities that's going to cause anything that moves across it to slow down. And so this is caused by any surface rubbing together. So anytime you have an applied force, there's always going to be a force of friction going against it. So any push or any pull will always have a friction force as the reaction pair going in the opposite direction of that applied force. I'm also told what the weight of the box is. And so I'm told what the weight of the box is in newtons. So the box weighs 2 newtons. And remember, weight is a combination of the amount of mass that an object has as well as the acceleration due to gravity. And gravity is always accelerating everything downward. So if I'm going to depict the weight of the box, I'm going to start at the center of the box, and then I'm going to draw an arrow pointing downward, and that's going to represent the weight or the box being accelerated downward due to gravity. So I can label this Fg for the force of gravity. You might also see it as Fmg sometimes. And we have a little reminder of all of these different types and ways in which gravitational force might be described in a free body diagram. So it's a measure of any force that's exerted on an object due to its mass and the value of g. So again, forces come in pairs. So assuming there's no special conditions, there should be a paired force in the opposite direction that's going against gravity. And so this one's a little weird. So this is what we call the normal force, or Fn, or F norm sometimes. So this is any force that acts on an object against a surface, and it's always perpendicular to the surface, not to the weight applied force that creates it. So I like to think of this as being a support force. You push your hand down on the table, you can feel the table up against your hand. So that's the normal force, the force of the table pushing back on you. Now, the normal force is generally even with opposite in directions with the weight force. So they cancel each other out. So that's why anything that is at rest on a table stays at rest on the table. So I have the weight on this binder clip accelerating it downward due to gravity, and the normal force that is opposing the weight of this binder clip that's going up from the table is equal in size but opposite in direction, so they cancel out. So this binder clip never crashes and falls through the table due to its weight, and it also never flies or pops up in the air due to the normal force. So these forces are equal in size, opposite in direction, so we have no net force, so they cancel each other out. So they're stationary in the vertical direction. So even though I'm not told that the normal force is 2 newtons, since this problem doesn't mention anything about the box also falling downward or the box being pushed upward or flying upward in the air, then I'm going to assume that these two forces are balanced, so they're equal in size but opposite in direction. So I'll be labeling the normal force also as 2 newtons. Now, last common force that's found in a lot of free body diagrams that is not found in our practice problem here is the force of air resistance. So this is a special type of frictional force. And as you know, as things are falling through the air due to gravity, while in our projectile unit we assume there's no air resistance, in real life there is air. So as it falls, that object is going to experience a little bit of frictional force caused by the air that's present, that's going to have it slow down at a mildly slower rate than as it would if gravity was not present. And that's always going to oppose the motion then of gravity. So it's going to be in the opposite direction. Okay, so you have attached this worksheet. Like I said, I figured we'd do a couple problems here together just to get you in the groove of things, and then I'll let you work on it on your own. And then I'm, of course, available for any questions. If you'd like me to send you a key so you can check your work, just let me know, and I'd be more than happy to do that. So here we're given a more detailed free body diagram. So instead of a box, I have a picture here. And I'm given a story. And this free body diagram is depicting all of the forces in the story. So I'm trying to identify which force is which. So I have a car is being pulled to the left by a tow truck. So in this free body diagram, what would all the forces be on the car? So first I have the pull force by the towing cable. So if the car is being pulled to the left, then the pull force is going to be whatever vector arrow is pointing towards the left. So if I look over here, I have my vector arrow to the left. Next to that is 5,800 newtons. So that's going to be my pull force. So any push or pull is going to have the force of friction acting on it in the opposite direction. And so opposing that pull force over here is 775 newtons. So that's the force of friction on the road. So now I have two forces, one going up, one going down here. And so one of these is going to represent the normal force. We're looking for the normal force. And the other is representing the gravitational force or the weight acting on the car. So weight, gravity, always accelerating everything downward. So whatever vector arrow is pointed downward, that's this one here, is going to be the gravitational force acting on the car. So this is going to be 14700 newtons. And then I can assume that this truck is probably being dragged across the surface. And so that surface is going to apply a force upward on the car against opposing the gravitational force or the weight of the car. So that's going to be our last vector here at 13,690 newtons. You'll have another free body diagram here for you to do on your own at your leisure, but hopefully that first one there is enough to get you started. Next up for 2, so we're finding the difference between balanced and unbalanced forces. So just a reminder, forces are balanced if they're equal in size and opposite in direction, and they're unbalanced if they are not equal in size or opposite in direction. And so an object will always move in the direction of an unbalanced force. So in this picture here, I have 25 up, 25 down, equal in size, opposite in direction. So these would be balanced and I wouldn't be moving up and down. Equal in size, opposite in direction. So these are balanced, these cancel each other out. So I wouldn't be moving either left or right. So this would be an object that would be completely stationary. It's not moving up or down or right or left because horizontal and vertical vectors are balanced. Here, vertically, equal in size, opposite in direction, so they cancel. So this wouldn't move up or down. However, these two are not equal in size. So they are opposite in direction, so they are going to cancel out a little bit. So 20 minus 15, that leaves me 5 left over. And on which side? So whatever side's bigger. So on the 20 Newton side. So this object would be moving. It would be moving 5 newtons. And it, would have a force on it of 5 newtons. And it would be moving then in the rightward direction, since that's the direction of the unbalanced force, or what we call the net force. So I'll let you kind of think about what these two are, and then you're going to group these into categories A, B, C, or D based on if they are balanced or unbalanced, and if they would be moving and which way they would be moving. This does have a back, so don't forget about the back. You're going to be matching up free body diagrams and stories. So give this assignment a shot. When you're done, you can send me a picture of it. And if you'd like a key so you can check your work, let me know, and I will send that back to you once I have a picture of this assignment from you. Again, you can answer questions on lined paper if you don't have any printers at home to print this off. But let me know if you have any questions, and hope you're all doing well.